Hello everyone and welcome. In this session, we will discuss the concept of depressurization, its role during fire scenarios, the meaning of adiabatic depressurization, key design constraints and standard recommendations, and finally, how Aspen HYSYS can be applied to model vessel depressurization. Let's start with the basic question. What is depressurization? Depressurization is the controlled reduction of pressure inside a vessel or process system. It is typically initiated during emergency conditions such as fire exposure or during planned shutdowns. This is achieved by releasing the process inventory, usually vapor, to a safe disposal system such as a flare or vent. The objective is not normal control but risk reduction. During a fire, a vessel is exposed to very high external temperatures. As the metal temperature increases, the mechanical strength of the vessel decreases. At the same time, the internal pressure increases because the contained fluid expands as it is heated. If no action is taken, this combination can lead to vessel rupture or catastrophic failure, such as a BLEVE. Depressurization reduces internal pressure and therefore significantly lowers the probability of failure. Now let's focus on fire case depressurization. In a fire scenario, the emergency shutdown system is activated. The vessel is isolated by shutdown valves, and the blowdown valve opens automatically. The purpose is to rapidly reduce the internal pressure so that even as the vessel heats up, the stress remains within safe limits. Fire case depressurization is therefore a safety function, not an operational one. Most emergency depressurization processes are assumed to be adiabatic. This means that the pressure reduction happens so quickly that no heat transfer occurs between the vessel and its surroundings. As a result, the fluid temperature drops rapidly due to expansion, mainly driven by the Joule-Thomson effect. This temperature drop is critical because it may lead to brittle fracture of carbon steel if minimum metal temperatures are exceeded. Depressurization design is governed by several important constraints. First, the minimum metal temperature must remain above the brittle fracture limit. Second, the vessel stress at elevated temperature must remain acceptable. Additionally, the blowdown valve may reach choked flow, which limits how fast pressure can be reduced. The flare system capacity, along with noise and vibration limits, must also be respected. These constraints must be balanced carefully to achieve a safe design. Industry guidance for depressurization is primarily provided by API 521. API 521 does not define a fixed final pressure. Instead, it recommends depressurization based on maintaining acceptable vessel stress levels during fire exposure. As a common practice, many designs aim to reduce vessel pressure to approximately 50% within 15 minutes. Although more conservative targets may be applied. Final pressure values, such as 7 bar gauge, are design assumptions, not API mandates. To summarize so far, depressurization is a critical safety measure to protect equipment during fire exposure. Fire case depressurization is rapid, typically adiabatic, and driven by safety logic. The design must ensure that both pressure and temperature effects remain within acceptable limits defined by material and mechanical constraints. This is where Aspen HYSYS becomes extremely useful. HYSYS allows us to predict pressure and temperature profiles over time, estimate blowdown valve requirements, and apply API 521 fire case correlations. While the tool is mainly used for initial or screening level studies, it provides conservative and safety-oriented results, which is exactly what we want in fire case analysis. Now, we will apply these concepts in Aspen HYSYS. We will define the process, fluid and vessel geometry, select the fire case depressurization mode, and apply the depressurization utility. This practical example will help connect theory with real engineering application. Let's start by creating a new case in Aspen HYSYS. Next, we select the components. In this case, the components are methane, ethane, and normal butane. Since our system contains only hydrocarbons, we select Pung-Robinson as the fluid package. Now we define the material stream. The operating conditions are temperature 55 degrees Celsius, pressure 40 bar gauge, mass flow rate 100 kilograms per hour. However, it's important to note that the mass flow rate is not critical in this emergency case because during depressurization, the vessel is already isolated by the shutdown valves. Next, we define the composition. Methane 0.5, ethane 0.25, N-butane 0.25. After defining the material stream, go to the Home tab. From the top ribbon, navigate to Blowdown and Depressurization, and then select Depressurization. This HYSYS utility is commonly used for initial or screening level depressurization studies. It generally produces conservative results, which is desirable from a process safety perspective. First, we specify the inlet stream by selecting the predefined material stream. If any warning message appears, simply click OK to proceed. Next, we define the vessel height, which is 1.5 meters. Software will automatically calculate the vessel diameter. Then we specify the initial liquid level as 15%. This represents a condition close to the low liquid level alarm, which is a reasonable assumption for a fire case. Software automatically calculates the wetted surface area, and we can leave it unchanged. Since this is a fire case, we do not perform a detailed heat loss calculation. Instead, we move to the Heat Transfer tab and set the operating mode to Fire, API 521. We leave C1 and C2 at their default values. For C3, which is a tuning factor for the wetted surface area, we specify a value of 1 to obtain conservative results. We also select the wetted area model as initial liquid level. This means the wetted area remains constant during depressurization, which aligns with API 521 fire case assumptions. For the heat transfer model, we select none. When using Fire API 521 mode, this is the recommended approach. Now we move to the valve parameters. Since we are depressurizing only the vapor phase, we select vapor flow only. For the flow equation, we choose the Mason-Allen equation. The critical flow factor is set to 1, representing choked flow, which gives conservative results. The valve CV will be calculated later. Under the Options tab, we set the PV work contribution to 100%. This ensures the predicted minimum temperature remains conservative during depressurization. We leave the recycle efficiencies at their default values, assuming thermodynamic equilibrium between vapor and liquid phases. Next, we go to the Operating Conditions tab. According to API 521, a vessel exposed to fire should typically be depressurized to about 50% of its initial pressure within 15 minutes. In this case, we apply a more conservative requirement and set the total depressurization time to 4 minutes. The default time step size is acceptable and can be left unchanged. In the vapor outlet solving options, we select Calculate CV. We specify initial CV value, 1 maximum CV step size, 3% maximum number of iterations, 100. This helps ensure stable and smooth convergence. For this example, a final depressurization pressure of 7 bar gauge is assumed as a conservative value, commonly used for thin-wall carbon steel vessels, while API 521 requires evaluation based on allowable stress at elevated temperature rather than a fixed pressure. After defining all parameters, we click the Run button. Once the simulation starts, strip charts appear, allowing us to monitor vessel pressure, temperature, and inventory versus time. Thank you for watching. If you're interested in learning new skills online, join our instructor-led online training sessions. For more information, visit our website, www.umsolglobal.com,